Bismillahirrahmanirrahim. Assalamu alaikum. I am Dr. Muhammad Zaman Ashraf. I welcome you all in reaction mechanism. Today our topic is mechanism of aliphatic nucleophilic substitution reaction. As I have discussed in my previous lecture, there are certain mechanisms which are present in aliphatic nucleophilic substitution reaction. The well known or the most commonly encountered mechanism are Sn2 and Sn1 mechanism. So first I will discuss the Sn2 mechanism. So today our topic is substitution nucleophilic bimolecular mechanism, Sn2 mechanism. So I will discuss what is Sn2 mechanism and the general requirement for the Sn2 mechanism. I will also discuss the evidences which support the Sn2 mechanism, because in case of Sn2 mechanism we call this bimolecular mechanism. Rate of reaction depends upon two molecules. So one is the substrate and the second is the attacking nucleophile. So in Sn2 mechanism we propose that the incoming nucleophile or the attacking nucleophile attacks from opposite side of the leaving group. It means the leaving group where present, the attacking group attacks from 180 degree. It means just behind this leaving group from opposite side. So when incoming nucleophile attacks from opposite side, so then we prove how this is possible, and we will discuss the cases which actually prove that this Sn2 mechanism is valid mechanism and incoming nucleophile attacks from opposite side of the leaving group. So let's start with the Sn2 mechanism. So in case of aliphatic nucleophilic substitution reaction, in the general introduction we write the general equation. Suppose we have this substrate and this Y is attacking nucleophile. The substitution nucleophilic bimolecular mechanism, this 2 stand for bimolecule. So it means the rate determining step, it involves the two molecules. So in this case, in aliphatic nucleophilic substitution reaction, we have two our reactants. One is the substrate and second is the attacking nucleophile. So when we write this equation, the Sn2 mechanism is one step process. So one step process means it never involves any intermediate. So in the single step, this attacking nucleophile attacks at the carbon, and in the same step this X it leaves. So it means this reaction it proceeds in one step, no intermediates are formed. This Sn2 mechanism, it involves a transition state. The transition state where the attacking nucleophile approach this carbon and the leaving group at the same time leaves. This is transition state, sometimes called activated complex, and then our product CY plus X negative. So this carbon, it is partially positively charged because it is attached with this electronegative halogen force, and this Y, it is negatively charged, or it possesses the unshaded electronic pair. So it must be electron rich, electron donor. So it attacks from this opposite side, and here you can see this situation in which transition state is formed. This central carbon, this carbon, it is now sp2 hybridized. It means this carbon, which is attached with 4 groups, 4 single bonds, it is sp3 hybridized. So when nucleophile approach this carbon, which is sp3 hybridized, then actually this carbon forms 4 covalent bond. When Y approach this carbon, then the 5th bond is formed. So actually in this transition state, this carbon, it is attached with 3 atoms. So 3 sigma bonds are present. So it means this carbon right now is sp2 hybridized. And at the same time, when here we have 2 lobes, suppose here we have 1 lobe and 2 lobes. So these lobes, they show that Y it forms this bond with carbon by overlapping with this lobe, and at the same time the bond which is present between carbon and X, this lobe, it leaves this X, and the bond between carbon and X is cleaved. Okay, so it means this carbon is sp2 hybridized. Right now this X is attached with the carbon. So this situation, it actually proves that the front side attack is impossible, because in the front side still no X is present. So that's why the chances for the attack of this Y from the front side is not possible. So that's why the one situation which is possible in this case, Y must approach this carbon from opposite side of the X, and here we have product and X negative. So this is the general situation of the mechanism which is Sn2. Now we give the evidences which prove that this reaction is possible when incoming nucleophile attacks from opposite side of the leaving group. As I told to you, this is one-step process. So when this is one-step process, the very convincing evidence is the kinetic evidence for this reaction. So when we discuss the kinetics of this reaction, kinetic evidence. So in kinetic evidence, the rate of reaction, when we write the rate expression, then we have rate is equal to, suppose we have K, and the first order for this Rx, you can write for this Cx Rx, and first order for this attacking nucleophile. So as a whole, this reaction is second order reaction. So the kinetics, they prove that the reaction is second order because this is one step reaction, and the one step, it means this is the rate determining step. So in rate determining step, 2 molecules are involved. So that's why rate of reaction depends upon the concentration of both substrate as well as the attacking nucleophile. Suppose in case when Y is present in excess, for example in some of the nucleophilic substitution reaction, Sn2 reaction, the Y, it also act as nucleophile and also as solvent. So in such cases, again the reaction is second order reaction like this, but we write the rate expression as K Rx. This is the case when Y is, suppose it also act as solvent. So because it is present in excess, again the reaction is second order. Such type of reaction which are one step reaction and Y act as solvent, they are known as pseudo first order reaction. Okay, this is not the first order reaction. This is known as pseudo first order reaction because this presence of this Y, it increase the rate of reaction. It play important role in the conversion of this reactant into product, but because of its large concentration, as it act as solvent, so that's why such types of reaction, they are known as pseudo first order reaction. So this is the kinetic evidence for this Sn2 mechanism. Another the most important evidence for this Sn2 mechanism is the stereochemical evidence. So suppose when this nucleophilic substitution reaction, your carbon at which nucleophile attacks, this carbon is chiral carbon. So it means when you carrying out the Sn2 reaction at chiral carbon, because this Y it attacks from the opposite side of this leaving group, then there is inversion of configuration. So complete inversion of configuration is observed in case of Sn2 mechanism, which is the direct evidence for this Sn2 mechanism. Suppose we have CH, here we have C6H13, here we have CH3, and here we have Cl. Suppose this is dextrorotatory enantiomer having positive rotation. So this is dextrorotatory enantiomer. It reacts with attacking nucleophile OH negative. So OH attacks from the opposite side of this leaving group, and we have the product C6H13. Here we have CH, and we have CH3OH plus Cl negative. As I told to you, this nucleophile, when it attacks from opposite side of this leaving group, if this reactant is positive, having positive sign for this angle of rotation, or it is dextrorotatory enantiomer, then this product it must be levorotatory. So this complete inversion of configuration is observed in Sn2 mechanism. So this is the evidence for this reaction. Such type of inversions, they are known as Walden inversion. So Walden it has observed the many examples in which inversion of configuration in case of Sn2 mechanism observed. So this is the evidence that the incoming nucleophile attacks from opposite side of the leaving group, and this carbon this carbon which is chiral carbon, if it is dextrorotatory after nucleophilic substitution in Sn2 mechanism, it is converted into levo, and if it is levorotatory, then it is converted into dextro. I mean, complete inversion of configuration is observed in Sn2 mechanism. I will also prove this by some experimental example. For example, we have CH, a chiral carbon, CH2 and phenyl. I write this, this is equal to phenyl. Common, we can also write as pH, or it is benzening. So this phenyl and CH2, this is benzyl group. Here we have CH3 OH. So this is it has the angle of rotation is equal to plus 33.0. So this is positive sign. It means it is dextrorotatory enantiomer. When it reacts with, suppose we have two routes, when it reacts with tosyl chloride, this tosyl chloride is like that. This is para-toluene sulfonyl chloride. Okay, so this hydroxyl, it attacks at this sulfur and remove this Cl. This is again a nucleophilic substitution reaction, but keep in mind that this oxygen attacks at sulfur, but this chiral carbon, it is intact. Okay, so carbon oxygen bond is not cleaved in this reaction. Only this oxygen attacks at sulfur and it replaces this Cl. Then we have CH, we have CH, CH2 phenyl, and O, here I write TS, tosylate. The Cl is removed, then here we have oxygen and all this group. Okay, so I write here TS because this abbreviation is used for a tosyl group, and here we have CH3. So it means this reaction in which oxygen attacks at this tosyl group and replace the Cl, and here we have tosylate ester, it never involves the attack of any nucleophile at chiral carbon. So that's why here retention of configuration observed. So it means the angle of rotation for this is equal to 31.1 degree. Okay. Then this tosylate, when it reacts with C2H5OH in the presence of base like potassium carbonate, or you can use here negative charge oxygen to increase the nucleophilic character of this hydroxyl. As I have told to you, the negatively charged species, they are more nucleophilic as compared to their neutral precursor. Then the lone pair add this oxygen, it now attacks from opposite side of this leaving group. Now your leaving group is sulfonate. Okay. So then we have CH and we have CH2 phenyl, CH3, and we have O C2H5. So this is ethyl ether of this alcohol. So in the conversion of this alcohol into ethyl ether, this step is the nucleophilic substitution reaction at chiral carbon, and here we have Sn2 mechanism. So that's why inversion of configuration is observed in this case, and its angle of rotation is equal to 19.9 degree. But right now this angle of rotation, it has negative sign. So this negative sign, it shows that the dextrorotating enantiomer is converted into levo-rotating enantiomer. So this is the evidence for Sn2 mechanism, which explain the complete inversion of configuration because the incoming nucleophile attacks from opposite side of the leaving group. Suppose another way in which this alcohol is converted into ether, suppose we have it reacts with potassium metal. So this potassium metal, it picks up this hydrogen, and we know that we can prepare the alkoxide of alcohol by reacting with sodium and potassium metal. If it reacts with sodium metal, then we have sodium alkoxide, and if it reacts with potassium, then we have potassium alkoxide. For example, if ethanol reacts with potassium, it will gives us potassium ethoxide. If methanol reacts with potassium, then it will gives us potassium methoxide. So alkoxide of this alcohol is prepared. We have CH2 phenyl, CH, O negative and K positive, CH3. This is simple, the formation of salt. So here again the carbon oxygen bond is not cleaved. It when reacts with C2H5Br. In this case, this oxygen, it acts as nucleophile and it attacks at this carbon, and Br is removed. Again you observe that your chiral carbon is intact. Okay, so here the nucleophile does not attack and replace any group. So that's why our product phenyl, CH2, CH, CH3, and here we have O C2H5. So this is dextro, again dextro, this is also dextro-rotating enantiomer, and its angle of rotation is equal to 23.5 degree. So this sequence of experimentation and the calculation of the optical rotation of this, the angle of rotation of these chiral compounds, they prove that in any case when Sn2 mechanism is involved, then there is complete inversion of configuration. The important is the attacking nucleophile attacks at the chiral carbon. If attacking nucleophile attacks at the chiral carbon from opposite side of the leaving group, then there is inversion of configuration. On the other hand, if any other group like oxygen or in this case when they act as nucleophile and attacks any carbon, then the chirality of this carbon, optical rotation of this carbon does not observe. I mean, it is not converted into another enantiomer. Dextro is not converted into levo, or levo is not converted into dextro. This is the retention of configuration. If I write here the retention or the inversion of configuration, this reaction, it does not involve the reaction at chiral carbon, so that's why here retention of configuration. This step, it involves the nucleophilic substitution at chiral carbon, and this attacking nucleophile attacks from opposite side, and it involves Sn2 mechanism. Then it involves inversion. Here we have this sequence. Again we have retention. Retention because the attacking nucleophile does not attack at the chiral carbon. So that's why the optical rotation of this carbon is retained. So this is the stereochemical evidence for this Sn2 mechanism, and this is most convincing evidence for this Sn2 mechanism, in which we propose that the incoming nucleophile attacks from opposite side of the leaving group. Another kind of evidence is, as we propose in case of Sn2 mechanism, this nucleophile attacks from opposite side of this leaving group. If we have some substrate which possess the leaving group, but in these substrate, if backside attack is not possible because of steric factor, then these substrates does not give nucleophilic substitution reaction. For example, if we have this, if leaving group is present at this bridgehead system, which is further substituted by this dimethyl group, then this is sterically hindered carbon. So if the attacking nucleophile is present, but leaving group is also present, this carbon is also partially positive charged, attacking nucleophile is also present, but the backside attack at this carbon is not possible due to steric factor. So it means if the Sn2 mechanism is correct, and in Sn2 mechanism the attacking nucleophile attacks from the opposite side of the leaving group, then this substrate it should not give nucleophilic substitution reaction. So here we have no reaction. So it means those substrates where leaving group is present at bridgehead carbon and where backside attack is not possible, such substrates never give Sn2 reaction, which is another evidence for the correctness of this Sn2 mechanism. Another such substrate is again we have the leaving group at bridgehead system. So when this is treated with any nucleophile, again suppose we have OC2H5 alkoxide, ethoxide, then again no reaction, which is another evidence for Sn2 mechanism. So in the third evidence in which we can prove the Sn2 mechanism, those substrate in which leaving groups they are present at bridgehead system and where backside attack is not possible, they never give nucleophilic substitution reaction. So these are the evidences due to which we prove the Sn2 mechanism. This is all about the substitution nucleophilic bimolecular mechanism. So as a conclusion, the substitution nucleophilic bimolecular mechanism, this is one step reaction. It never involved any intermediate. The transition state is involved. Transition state where the leaving group leaves and at the same time the attacking nucleophile attacks or form the bond. So it means this is the situation where both the species they approach the carbon, both the species they attach with the carbon, and it proves that the attacking nucleophile it cannot attack from the front side where the leaving group is present. Only one situation which is possible, the attacking nucleophile attacks from opposite side of the leaving group. So if this is one step reaction, then when we observe the kinetics, we have second order kinetics. Rate of reaction depends upon two molecules. That's why this is known as bimolecular mechanism. Then another kind of evidence is the stereochemical evidence, where we observe the complete inversion of configuration. And the third evidence, where we have the substrates in which leaving group is present at bridgehead system. Such substrates, they never give nucleophilic substitution reaction. So this is all about the Sn2 mechanism. In my upcoming lecture, I will discuss the Sn1 mechanism. Thank you very much.